All right, so we'll talk about the confidential computing, capability that we're working on for RISC-V platforms. I'm Ravi Sahita. I work at Rivos. In the past life, I've worked at Intel for many years, and I'm also the co-chair of the security HC with Andy Dello, and then one of the TGs for that's working on the confidential compute. So thanks for joining. Let's see, we'll try to keep this on track. I have a lot of material, so I'll go fast on some topics. Feel free to catch me after the talk if you have further questions. But I'll try to give you a good picture of what does it mean to enable confidential computing, what does it mean for RISC-V platforms in terms of what is the potential impact on the ISA. There's a task group that's looking at the ISA aspects. There's also task groups looking at the non-ISA aspects, which cover the software ABIs, for a couple of generation of the confidential computing, and then we look at some of the platform-oriented aspects as well. So just a quick intro, I'll do a fast intro to confidential computing. So there has been a lot of work in the last, I would say, 4 to 5 years, starting around 2015 when the first sort of practical implementations for confidential computing showed up. It's basically a model of using a trusted execution environment to protect the data while you're performing computation on it, right? So previously, obviously, there's been a lot of work in the past on protecting data while it's at rest, through various encryption integrity mechanisms, cryptography mechanisms, and also protecting it on the network while it's being sent from one point to the other. And the last area, and we saw a couple of talks today morning that talked about a lot of the data breaches and the threats on data. So one of the ways we can solve that data breach is really cut down the trusted computing base that we rely on to process the data, right? And not just protect the data while it's in storage or it's being sent over the network, but also protect it while you're computing on it, right? And that actually enables a lot of use cases, right? You can do a lot of interesting multi-party secure computation use cases. Obviously, it can be used for protecting your IP, which could be your code or data. It can protect against various insider threats, depending on how you design your confidential computing system to protect against insider threats, et cetera. And also to protect your reputation, et cetera, against, when you're trying to apply privacy regulations and address, various government and other industry-specific regulations. So when we're thinking about confidential compute, you really have to consider sort of 3 areas from a threat model perspective, right? And when we started working on confidential compute, we sort of sat down and wrote this threat model in a good amount of detail. And it really covers these 3 aspects, right? You have to think about what is the attack surface that you're targeting. And so what are the different areas of impact that can affect your data in use, right? It could be the software itself, the protocol being used to carry your data around, the various cryptography mechanisms you're relying on if you're not using them correctly with the right key strengths, et cetera. Side channels, supply chain, even hardware attacks, right? You also have to think about, for those vectors of attack, what are the capabilities the attacker has, right? Are they using only software? Are they attempting hardware attacks? Are they attempting more, involved nation-state supported attacks, right? And also in terms of the deployment models or the use case where you're applying that confidential compute paradigm to your data protection. So now, when we look at those attacks, we also can look at some things that sort of are, remain common in terms of requirements. Like, what does it take to build a trusted execution environment so that we can sort of uncover what would we need in terms of ISA and non-ISA capabilities on the RISC-V platform, right? So this definition of a trusted execution environment sort of has been debated a lot, and there's a consortium called Confidential Computing Consortium that sort of uses these main requirements as sort of the core requirements. And there are a couple other requirements, but I chose to focus on these like primary required ones, right? So the first one is data confidentiality, and you can achieve that through various mechanisms like applying access control on the system or against physical attacks by using cryptography mechanisms, right? The second one is code integrity mechanisms. So you want to make sure that you're actually executing the algorithms that you wanted to execute on the data that you're trying to protect, right? And again, you can apply access control, cryptography mechanisms, additional authentication mechanisms. There's data integrity, right? Which is making sure that as you're processing the data in use, you're getting back what you wrote as the actor operating on that data, right? And again, you can apply access control, cryptography integrity mechanisms, authentication, or also if you're storing the data associated with that entity that processed the data, as well as sealing. Last but not the least, a very important cornerstone of a confidential computing implementation or architecture is an attestation model, right? So if a relying party that owns the data that's being processed cannot prove that the trusted execution environment is operating with the TCB that they expect, then you don't really achieve that important property that confidential computing is trying to achieve, right? So on one end, you have all these mechanisms that let you build up your infrastructure to support that TCB, and on the other end is the attestation model, which helps you prove that you're relying on that TCB, right, or that trusted computing base. So let's peel that further a little bit, and let's look at it from a sort of a reference architecture model, right? What are the security goals and what are the functional goals we want for such a trusted execution environment? And then we'll sort of dive into the ISA and non-ISA aspects. So the first thing is to start from a well-managed and well-trusted, potentially signed by the hardware manufacturer or silicon manufacturer, a hardware-based root of trust. Right? That is sort of the beginning of your trusted computing base, and a lot of the mechanisms that we talk about in terms of strong cryptography mechanisms are rooted in that strong TCB. From there, we can think about, from a design perspective, really partitioning how systems are managed on the platform. And this model can be applied to embedded systems as well as high-end data center class systems, right? Where you want to try and separate your resource management, orchestration capabilities, and free them and decouple them from the security properties you're trying to achieve, right? So that's sort of this partitioning of these roles, right? And I'm showing here an example of like a VMM or OS running on the left-hand side doing resource management of ordinary legacy VMs, and then a confidential VM environment running on the right-hand side with the support of a TE security manager, right, which owns the security properties. We also want common interfaces between these components as common as possible, right, that map back to the ISA mechanisms that we can provide on a RISC-V platform that support these access control and isolation mechanisms, right? Those common ABIs also allow us to back those up with open auditable implementations that somebody can reason about. Because from a security perspective, we want capabilities that are responsible for security to be as transparent, open, and auditable as possible. Then, depending on the threat model that we looked at in the previous slide, you probably want other extensions that the architecture supports. Like if you're addressing a physical threat, you may want to protect your memory that's leaving the SoC or the platform with additional cryptographic mechanisms to protect the data while it's being processed through memory. Right? And there may be many forms of memory devices. Also, we know that we are not limited to RISC-V processing being only on the CPU. It may be in other accelerator devices, and we want to make sure that those devices are covered as well from a confidential computing perspective. So that gives us these functional goals beyond the security goals, is to encompass all these processing elements, right? Try to avoid or reduce the amount of app refactoring we have to do so that we can bring a lot of these workloads, benefits of confidential computing to existing workloads without having to go back and like refactor your workload and rewrite your libraries. And also retain compatibility with a lot of the other industry standards that are happening at the same time as we are building this here for RISC-V. There are other architectures that support confidential compute as well, and there are other standards in the PCIe SIG, in the CXL SIG, that are building capabilities on devices that are compatible with this trusted execution model. Right? So we want to make sure we work with those interfaces and those standards. So we look at these three areas. Let me see how I'm doing on time. So I have about 9 minutes. So I'll kind of walk you through these three areas. The first one is what are the current TGs working on in terms of the ISA to support this confidential computing model? What are the non-ISA TGs that we have that focus on the SoC capabilities or the ABI capabilities? And so I've split the non-ISA into a hardware and a software. So we'll try to cover or touch upon at least, give you an introduction to all three subtopics. So let's dive into ISA. So this is sort of like the lay of the land today, right? We have, I'm not showing H extension here, I'll cover that in a second, but we basically have these three privilege levels on any system, and the OS of the VMM basically has access to the full system, right? So including the M mode firmware, it basically covers, from a TCP perspective, that's your entire TCP. There's no separation per se between these roles. So the first ISA mechanism that one of the TGs is looking at is called supervisor domains, right? So this is an access control capability that's driven from M mode, right? So hence it is called SMMTT, right? It adds a memory tracking table that essentially allows you to build differentiated trust models, where you can use the existing PRIV ISA, which is already ratified in RISC-V, and also potentially leverage the hypervisor extension, which has already been ratified, to extend that in an elegant way so you can create these trust boundaries on the platform, where you can host different forms of supervisor domain managers, right? So in this picture, at the root, I'm showing this M mode, which is called a root domain manager. And then in each of these supervisor domain silos that are created, you can use the existing ratified PRIV ISA and institute a supervisor domain manager in each of these. So you can consider like the leftmost supervisor domain manager being like the default, which is doing resource management, and then create separate supervisor domains for the different instantiations of the trust models you want. So I could have a supervisor domain that supports confidential VMs or confidential apps, and then I could have a separate supervisor domain that supports a trusted execution environment that I need for devices, and so on, right? So it gives us immense amount of flexibility to support those kinds of different use cases. But in addition to that base ISA for the memory tracking, we need a couple other pieces for this to really hold water in terms of interacting with devices, with interrupts, interacting with debug subsystem, and so on, right? So those sub-extensions are also being worked upon in this TG. And further, once we define this architecture, the software ABI sort of can take it from there and apply the system-specific policies that you need to apply on such a system. So what is the motivation behind a memory tracking table when we have things like PMP and ePMP and so on? An important point to note here is that the kind of domain we are targeting with confidential compute, you're interacting with rich OS environments, right, which have really complex memory managers that are built over many years, right? And those kernels and VMMs are managing memory at page granularity, right? So we support different architectural sizes for page granularity, and we want to retain that model, but with the separation of the resource management and the security that I was mentioning earlier, right? So a memory tracking table-like structure gives us this flexible model where we can move things, we can move memory resources between these supervisor domains in a flexible manner. That's supported by the ISA through additional mechanisms of memory tracking, which essentially is a table that says, if I get a physical address, the architecture will enforce a property of access for a supervisor domain through that memory tracking table for that physical address, right? So once your address resolves through your address translation mechanisms, your first stage tables or your second stage tables, the MTT will enforce whether that physical address is allowed to be accessed in the context of that supervisor domain, right? And then you can define a lot of interesting software ABI conventions that allow you to change whether that ownership of that page changes between one supervisor domain or another, right? And that's really that's where really the ABIs come in. So this is just showing an example of applying that supervisor domain concept to existing software stacks, right? So on the left-hand side, we're showing Keystone, which is a confidential computing consortium project. It's a sandbox project there, right? Which shows how a security monitor can essentially create app-level enclaves, right? On the right-hand side is the CoVE ABI proposal that we've been working on in one of the TGs in the security HC that shows how you can use the H extension in addition with the supervisor domain to host confidential VMs, right? So they have very similar sort of properties and can use the same ISA mechanisms. So this chart just shows like a quick cartoonish view of like where the memory tracking table shows up in the access control model. So you may have a first stage page table active or not, depending on the modes you're using. You may have a second stage or a G stage page table active if the hypervisor extension is enabled. But then finally you apply the memory tracking table to check whether for that active supervisor domain on that heart, whether that access is allowed or not, right? And this composes nicely with the SV page table extensions. So you can keep all of your memory permission model as is inside that enclave runtime or in the confidential VM, and impose only the access control property through the memory tracking structures. And here, this is an example of like how we can leverage that MTT model to seamlessly bring in attaching interrupt files to supervisor domains, right? So if you know of the advanced interrupt architecture or the APLIC architecture, when you have a supervisor context, that supervisor context manages the supervisor interrupt files, right? When you have multiple supervisor domains, you really don't want the supervisor domains to be aware of each other, right? Because they might be like completely different context. They're hosting confidential VMs, or they're hosting trusted execution environments. So using this model with very simple extensions to the M mode CSRs, right? We can allow the M mode CSR to essentially control how supervisor domain interrupt files are mapped to supervisor domains, right? And use exactly the same mechanisms of this new MTT structure or a PMP structure to access control that memory interrupt file, the S mode interrupt file. Once we've done that, the advantage you get is that now the M mode can still mediate between how these S mode interrupts are delivered through those S mode interrupt files. Additionally, they can they can basically keep the interactions of that supervisor code within the supervisor domain exactly the same as the existing interface through the IMSIC CSRs as shown in the bottom. So we don't change the code that somebody's written in the supervisor domain to interact with the S mode interrupt files. We only change the access control properties that the M mode software can apply on how those interrupts are delivered into those domains. So that gives that M mode TCP control over how interrupts are bound to specific interrupt domains. And that's an important baseline function that eventually when we get to assigning devices to these supervisor domains, we will leverage this capability to also make sure that interrupts corresponding to those devices are safely injected only for the domains that own those devices. So I might be running short on time, so I'm going to go a little bit fast through the non-ISA just to give you guys a sort of a quick preview into this. So one of the non-ISA elements we are working on is called the IOMTT. So this is a non-ISA capability since it doesn't have any ISA relevant interfaces, but we're introducing this notion of an IOMTT checker that works in conjunction with the recently ratified IOMMU, right? To basically show you how when an access comes in from a device, it can be essentially classified through this IOMTT checker and can be associated with an IOMMU so that it can use the exactly same ratified IOMMU page walks, but in conjunction with the MTT structures whenever physical addresses are reached as part of those IOMMU walks, right? So this allows you to maintain that property of physical memory isolation between the supervisor domains without changing how your IOMMU translations are happening, right? To resolve a IOVA to a system physical address. A couple points here. So this is on the debug and the machine monitoring. This is an area where there was a recent secure debug TG that was just formed in conjunction with the DTPM SIG, where we want to put some controls around how you secure the probe-most debug, and which is important from a confidential compute capability that once you have a supervisor domain for confidential compute, you can't just arbitrarily allow an operator to turn on probe mode debug for it, right? So it's important to put in some mechanisms to access control and authenticate how your secure debug happens. On the hardware root of trust, I wanted to just call out sort of the, how it can be used to extend the attestation mechanism or support the attestation mechanism. And really what this slide is showing is starting from your first immutable instruction that executes in ROM in the hardware root of trust, how it can be extended essentially through a layered attestation model to reach your final, the confidential VM or enclave that's running on that platform, right? With the idea being that confidential VM, which is called the TVM in this picture, can interact with a relying party and prove to a relying party that it is holding attestation identities that route all the way down through this TCB into the hardware root of trust, right? So when a verifier challenges that confidential VM or TVM, it can verify that it's relying exactly on the TCB that consists of that TVM, the TSM or the TE security manager, the ROM and the M mode firmware, and that hardware root of trust, right? And none of the other resource manager, operating system, VMM code that's running on that hosting platform. And OpenTitan is a good example of an open silicon root of trust, sort of following the same principles of transparency and auditability. So Okay. So on the non-ISA, I just have 2 more slides. So I wanted to give you sort of a quick bird's eye view into where the CoVE IO ABI is and the CoVE ABI and the CoVE IO ABIs are at. So the ABI basically sits between, so I'm showing an example of 2 supervisor domains here, right? And the ABI essentially sits, so let's see if I can use the laser pointer. So the ABI essentially sits here between the host OS confidential domain manager, the resource manager, and the TSM, which manages these confidential VMs. And there is a second part of the ABI that sits between a confidential VM and the TSM, right? So to give you a quick bird's eye view into these ABIs, which are currently documented in the CoVE spec, you'll basically see these aspects of the ABI that cover the entire lifecycle of a confidential VM. So starting from like a pre-built stage where you might assign the memory as a baseline function to the confidential domain, and then carve out memory from that assigned memory for that confidential domain to specific confidential VMs, right? And as the TVM is running, you might be doing things like moving some memory back to the hosting domain as shared memory, or granting specific access to specific memory to the host to emulate devices and so on, right? So there are a bunch of functions here. Again, we don't have time to go through these right now, but I invite you to look at the CoVE spec where these are described in each phase of life cycle of that the confidential VM. And again, the POCs are built in such a way where you can support wide variety of applications, all the way from an embedded platform to like a data center like usage when you're running confidential VMs. So given the lack of time, and I don't want to hold you back from lunch, you can always look at the couple of slides that I skipped. I wanted to end with this sort of call to action that really, from a RISC-V platform perspective, if you look at it in contrast with other competing architectures, confidential computing is an important cornerstone that we need to build the right mechanisms for, that gives us flexibility for the deployment of RISC-V in these different kinds of use cases, right? And I also invite folks to join the active TGs. Like I said, we have 2 non-ISA ABI TGs and 1 ISA TG that's focusing on confidential compute, as well as POCs and things like that. And I have a bunch of references to the POCs at the back of these slides. So folks can look at that and join the active work in that area. Thank you.